Yeah, so welcome to my presentation. 1 minute, please. So, yeah, welcome to my presentation, Archetypes of Digital Twins, which was published in the Business Information and Systems Engineering Journal in 2021. So today, I will talk about our motivation to do the research, give you a brief foundation about digital twins in mechanical engineering, present our research design, our results, and conclude the presentation. We have started our research in the winter 2019 and 20. Why is it so? Winter 1920, and at that time, there was a huge peak of interest for the topic of digital twins in mechanical engineering and logistics. And as you can see on the right-hand side, the Gartner hype cycle said that the topic of digital twins will reach the plateau of productivity within 5 years. The cycle was from 2018, so next year it should reach the plateau. And looking at the literature, you can see a huge incline in a huge growth of literature about digital twins within the last years. I just brought you the graph until 2019 because at that time we did the structured literature review. However, the number of publications grew exponentially as well in 2020 and 2021. But if you are dealing with the topic, if you are dealing with the topic, you can notice that there's not an ambiguous understanding of digital twins because there are several definition streams and research streams which define their digital twin in a certain way. Starting with the simulation of material flows, from this section, the digital twin is seen as an evolutionary step of simulation, so that is a new kind of simulation models. And that goes in hand with the NASA, who say a digital twin is a multi-physics, multi-scale, probabilistic simulation. Whereas if you are talking with guys more going to the product lifecycle management, they see a digital twin as a set of virtual information that describes your physical product and that connects the virtual world with the real world and synchronizes it. So there are many definitions. If you are looking at 50 different publications, you will at least find 25 different definitions of a digital twin. So we try to structure the field of definitions and to come up with a more global definition. So for our motivation and research questions, talking with people, it is always the first question, what do you think a digital twin should look like or looks like? And everyone answers with a twin is a digital picture of my asset, but, and then it differs. And for example, it differs in the style of information. So is our digital twin just some kind of a data repository, or is it a real-time representation that can do something with its data? So, coming to the research questions, the first one is we try to look at are there any clusters of digital twins which are more prone to a certain sector like healthcare or like logistics or automotive industry, or is there a general cluster of digital twins? What are design characteristics of digital twins in practice and in research? Are they differing between research and practice, or are they the same? And the third question was, what are archetypes? So describing clusters of digital twins. And to understand the concept a little more, I've brought you the 6 most used definitions of digital twins, and as you can see, the first one is from the NASA with the multi-physics simulation. The second one is from Dr. Michael Greaves, who coined the term digital twin in the beginning of the 2000s. And he says we do have a physical product in our real space, we do have a virtual product in the virtual space, and we do have a bidirectional data linkage between both. And Rosen, as the third most used definition, says it's the next step of simulation. But as you can see, they are quite similar, but not exact the same. So coming to our research design, we applied a mixed method research. We started with a structured literature review, and from that we developed a taxonomy, so a morphological box of the different descriptions of digital twins. We then conducted a first set of interviews with industrial experts from Central Europe, and we clustered both the taxonomy stemming from the literature corpus and the results from the interview series. So we had several cluster patterns, which we then triangulated, and that concluded in a certain set of archetypes, so defining patterns, which we then evaluated in a second set of interviews for their practical usability. Starting with the SLR, following Webster and Watson and von Brocke et al., we searched for the term digital twins in the databases ACM, ISIL, IEEE, and Science Direct and JSTOR. And at that time, in the winter 1920, we yielded 579 papers. If you do this search now, you have more than 10,000 papers on that topic. We then restricted our search to the term digital twin in title, abstracts, and keywords to have a more closer look. That yielded in 382 papers. We checked for accessibility, quality criteria, for example, comprehensive argumentation and duplicates. And we checked in a full text review that the digital twin is really the core element of a paper, not just a side notice. So we had 194 papers, and doing a backward search, which papers these 194 cited, we had in total, in the end, 233 papers. With these papers, we did a taxonomy design after Nickerson, so we had our 7-step approach. For the literature corpus, we did the lower one, the empirical to conceptual way, so we identified a subset, we analyzed it, we identified characteristics, we grouped them, and finally we had our dimensions and characteristics. And for the interviews, we did it the upper way, the conceptual to empirical way, but both yielded in a taxonomy. The interviews were 18 interviews, 15 for the data acquisition with experts from different sectors, as I've said, healthcare, automotive, logistics, producing companies, infrastructural companies like Deutsche Bahn and electricity network providers. And we did 3 interviews as evaluation. Each interview was transcribed and recorded, and we aimed for a semi-structured approach so that we had a discussion. For the archetypes, we checked whether there are any cluster types. We eliminated non-relevant clusters, which I will show you in a second, and we synthesized the remaining ones, checked for doublets, named them, and explained them. Before I come to the taxonomy, we do need to know that there are 4 types of characteristics. So we do have the mandatory ones, so these are necessary for a digital twin. Otherwise, we are talking about another concept like a digital shadow or a virtual model. We do have mutually exclusive dimensions, so we need the dimension, but which characteristic we choose is open. We have the not relevant ones because these characteristics were so general that they do apply not only to digital twins and their archetypes, but to all virtual concepts. And we have the optional design characteristics. These are responsible for the differentiation between the different archetypes. And now coming to the taxonomy, you can see we have 3 meta dimensions and several dimensions with at least 2 characteristics each. And as you can see, there are some characteristics which are mandatory for a digital twin. For example, we do need an automated data acquisition from our real-world counter twin, we do need multiple data sources, and that does not mean that we do need multiple sensors on our real world, but we do need sensors, we do need applications, we do need historical data and so on. We do need a synchronization, and we do need raw data as input directly from our real-world application, and everything has to be bidirectional. So we do need an automatic data flow back to our real world. We have the option of human-machine and machine-to-machine interfaces for downstream systems. We do need interoperability, but whether it is via translator or fully is well, open. Unfortunately, if you're looking at the practice, many twins and many virtual concepts are not interoperable at all, and that is a huge problem. The purpose is, well, saying what are we doing with our data within the twin, and we deemed it mandatory that the digital twin can process the data internally. So it is not just a data repository, but you can simulate, you can analyze, you can optimize with the data within the digital twin. And the last meta dimension, the conceptual scope, it was a meta dimension which was relevant for the literature corpus, but it is not relevant for the archetypes, because in practice it is often not easy to say what do we need. Do we need an identical twin? Do we need a partial twin? Because there are use cases where a partial twin is sufficient, and then an identical twin is just too costly to implement. It's the same with the time of creation. It's not always easy to decide, do I have our digital first? Normally, if I start with a product today, I do have a digital picture before I have any physical copy. But if we are looking at supply chains, if we are looking at factories, which are brownfield applications, we do have a physical component first. Into this taxonomy, we sorted 250 digital twins, 230 coming from research and literature, and 15 coming from the industry. And each twin was configured otherwise, but we were able to gain some clusters. In total, we got 10 clusters using our studio, and as you can see, if we are looking at the mandatory characteristics, there are some clusters that do not possess all mandatory characteristics. For example, it's cluster 1 and cluster 2, which are not synchronized with our real-world application. So we deem these both clusters as not digital twin-like. If you are more interested in which concept this cluster's pictured, I can only suggest that you look at the journal because it's more detailed in there. But mostly it were just virtual models, digital shadows, digital threads, or just some kind of data repository if a mandatory characteristic was missing. So the clusters 1 and 2, and as well the clusters 6 and 9, which were the same cluster, but one coming from the literature, one coming from the interviews, were not able to describe an archetype, but the clusters 3, 4, 10, 5, 7, and 8 were able to describe a digital twin. So we do have 5 different clusters, so possibly 5 different archetypes. And if you are looking at the clusters which are remaining, you can see that they distinguish themselves in certain characteristics. So we saw it justified to continue with 5 archetypes. But you can also see that these 5 archetypes are some kind of a maturity index. So they are building upon each other. The first archetype, which is represented by cluster 3, is some kind of a basic digital twin. So we do have our mandatory characteristics. We do have synchronization, we do have a bidirectional data linkage, but that's it. Nothing more, nothing less. The next archetype is the second one, the enriched digital twin. So it has all the mandatory ones. It is archetype 1 plus we do have the option of a semi-manual data acquisition. And that is important, especially if you're looking at infrastructural use cases, because by law, it is mandatory that the people can intervene and interfere with your virtual copy of your system. So you cannot say we do have a fully autonomous and fully automatic system in, for example, rail network management. The third archetype, cluster 8, is the first one which can be seen as a fully autonomous control twin. So it has all the characteristics from archetype 1 and 2, and it is able to directly manage your physical system via this digital twin. So you do not need any person to overlook and to do the management himself. But for the autonomous control twin, at this point, or starting from this point, we do need interoperability, at least via a translator interface. The fourth archetype, represented by cluster 5, is the enhanced autonomous control twin. So it enhances archetype 3. And at this point, we are able to include downstream service systems. For example, we do have a simulation inside our digital twin, but we can yield the results from the simulation to other software products which are located downstream. They do the analyzing, they do the optimizing, they yield their results back, and the digital twin is coming up with a management strategy based on this optimized data. And the last archetype is the exhaustive twin, so it has all the potential design characteristics, and it's a solution, which can be applied at many use cases, but at the same time it is very complex and very costly to achieve this level of a digital twin. So in general, as we have asked in our evaluation interviews and in talks with other industrial experts, it is not necessary to achieve for archetype 5 if your use case do not request it, because maybe you can do whatever you want with archetype 3 and then you should use it because it's cheaper to get. Transferring these archetypes into a picture, we did define the ecosystem of a digital twin like this. So we do have our governance and interoperability space, which includes all the physical system, the virtual representation, and the external data sources and data repositories. We do have an ongoing synchronization of raw data coming from our physical system directly into the digital twin, which consists of our virtual model as the digital representation, internal data processing capabilities. Most use cases used simulation analysis and optimization, but there are also some use cases who use a digital twin for monitoring purposes. And there it is the question whether it is wiseful to use such a powerful tool just for monitoring. And of course, we do need an internal repository. But the synchronization also goes to the external data processing units, to external databases, especially for historical data. And we do have the option to include external data apps, for example, weather forecasts for the chemical industry or traffic updates for the logistics sector. So, coming to the conclusion. For the first research question, are there any clusters? Yes, there are 8 clusters, which can be seen in the research field of digital twins. However, only 5 of them are related to the topic of digital twins and do describe a digital twin. So we have 5 archetypes, so describing clusters of a digital twin. We structured the body of knowledge and the whole different research streams are combined independent of your sector and of your use case. As always, with structured literature reviews, and if you do a coding, which is necessary for the clustering process, it is subjective, but we did our best to minimize these influences. And beside the option for practitioners to model their digital twins in the industry accordingly to the 5 archetypes, and to have a way to get from archetype 1 to archetype 3, 4, or 5, whichever is necessary. The scientific contributions show further ways of research, building up on these archetypes, for example, design principles, which my colleague just published in the CAiSE journal as well for shared digital twins. Further research possibilities are reference models and concrete implementations and instantiations of digital twins. So, thank you very much, and questions, please.
Okay, thanks for your interesting talk. Actually, it refers to a doubt I've been having for some time. And I would like to ask if you help me, because I missed, because you presented lots of information about your approach to derive the archetypes. So I was thinking about an example of an agent-based platform that is used for social interactions, for analyzing, for instance, crowding aspects. For instance, we are using one by a French team called Gamma, which allows you to model with a DSL the behavior of agents with using a domain-specific language, where, for instance, you can model the social interactions individually or in groups and so on. So such kind of my question is this a twin-based approach? Because we have a twin with the physical space, because we pick up, for instance, maps, geographical information system maps as an input. So there's a twinning on geographical space, but not a synchronization with what is going on currently in the space that we are trying to derive simulations. So my question is this a digital twin, and if so, which kind of archetype does it match?
Yeah, that's an interesting research question we are doing research on right now as well. The problem is you need to define your physical space, and if you have, let's call it, agents in your physical space, like I think you said touristic sector, you have, your agents would be people visiting a place or something like that. You do need some kind of a virtual representation of that, and then you can use, we are thinking that it should be useful to use this agent-based modeling within an ecosystem. And the open question that we have, and honestly I do not have an answer for that, is whether there is a digital twin of each real-world person, or is the whole ecosystem the digital twin? In the second option, it is, I think, more thinkable. It is easier to visualize that you have a digital twin, and within the twin you do have several data sets which represent a real-world person. The other way, you do need, if a digital twin is one person, you do need some kind of an orchestrating mechanism. For example, in data spaces, federated data spaces, so that you do have your data sets in this cloud, and but they do need an orchestration, and it's an open topic for us. So,
just expanding a little bit on this exact question, because what you're doing is, it's essentially bottom-up, right? So you're structuring things from what you found in the literature. However, often there are questions which are not answered in the literature, and one important question is this one. So digital twins, what kinds of things can have twins? So what kinds of things twins can be twins of? So clearly physical objects, maybe events, maybe certain reified properties, like, for example, you want to trace the knowledge of an agent about something. Or if we don't stay in this dichotomy of individuals and types, maybe types themselves can have twins. So instead of, I can trace what happens with a specific tumor, but what if I trace what happens with the tumor type, the evolution of concepts and things like that? So is that under your radar to investigate also this fundamental questions that perhaps are not answerable via a bottom-up approach?
Definitely. Especially if you're looking at healthcare applications, you do have this mixture of twins of patients, twins of hospital, twins of diseases, and everything is called a digital twin, but is it one? So yeah, I think we would be good advised if we have a closer look on the real-world applications in industry, in healthcare, and so on, and come from that perspective as a second research stream, and then we have to match our theoretical works, which I have just presented, with the real-world influences. So
then we get to this demarcation problem Bernard was talking about before, which is differentiate case in which people are just using the label, right? But it's not really a digital twin, or wouldn't be warrant to call that a digital twin, right? So you have a criteria for deciding if these are not just active models or things like that.
Yeah, I think the criteria are the mandatory characteristics. So we do need some kind of constant data input, data processing, and data feedback to our real-world system. And then we can, I think we can talk about a digital twin, whether it's a system or an agent. It's you have to define in the beginning in the conceptual model what are you looking at, and that is then your real-world application.
But then you're saying it could be data about anything, about types, about events. Okay, that's a nice answer. I would agree to that. Yes.
I suppose that digital twins can exist before their physical twins. But it seems that some of the definitions seem to exclude that, because they were formulated like, well, a digital twin is a copy of its physical existing twin or something like this. So I had the impression of some of your example definitions that they seemed to suppose that the physical twin is already there, while I suppose it is often the other way around.
Yeah, in practice it is often that, in fact often so, that we do have our physical copy because the digital twins are retrofits.
No, but the point is, it must be like this according to some definitions. There is a physical twin, and then we make a digital twin. While I said, I think that definition is wrong, because it should be possible the other way around.
It should be possible, and it should be done so. So if we start with a new thing, a new life cycle of a twin, we should start with the virtual and digital world.
Yes.
And that is a huge discussion which we had last year on a conference where exactly this point said, okay, many people say we do need a physical part and then we get our digital twin, but that should not be the way it should be done.
No, because I suppose that in a lot of applications, you do the digital twin in order to understand your future physical twin.
Yeah.
Yes. So actually, so what you could have done, because there were 50 definitions, if you do kind of definition engineering and adapt that one, then you probably come back on one or the other of the other 50 definitions, wouldn't it? Anyway, to get some, do some definition engineering might be interesting with 50 definitions.
Yeah, I think we should do that in the next paper.
Some final questions? People are hungry. Give you once, twice, no? So let's thank Hendrik. Thank you.
Thank you.